All right, here we go. Reaction video number 9. It's a Friday, so I'm excited to wrap up the week. And I think I found something. It looks like we've got pulleys on an inclined plane or something. So this looks exciting. Let's get started.
All right, so I'm going to number 7 on the homework 6-2. There were lots of different perspectives from which to look at this. I chose to look at it from the perspective that the change in the potential energy equaled the change in the kinetic energy.
I like the fact that she said there's multiple ways to do it. That's really cool.
The change in potential energy is going to be the change in potential energy.
So the way that she's written this is fascinating, right? You could add potential energy to both sides, and you could, basically say this, hey, I'm just talking about conservation of energy. And so if you say conservation of energy just means that all the total changes has to be 0. But she's written it a little bit differently, right? She's like, look, we can take that expression and we can think of it differently. If we want to know, for example, I guess I don't know what the actual problem stated is. Oh, maybe it's just this V here. Sorry, this V here. Sorry. I think that if we want to know something about speed, probably that means wanting to know the kinetic energy. And so really isolating that and saying, okay, well, good Lord, all we have to do is figure out how much the potential energy changes and we'll be in business. And so I think that really isolating the thing that you want right away is fine. I would imagine that most students could handle the fact that this is the same thing as the change of all the energy is 0. This negative sign might start freaking people out, but it's funny when I teach this stuff, sometimes I say, if the negative signs are freaking you out, just get rid of them all and do just the absolute values of everything, for problems that don't go crazy. And at the end, just ask yourself, should this have been going fast or slow? Should it have been going up or down? Should it have been going right or left? And if you can convince yourself through other means that you know the direction of the answer, then boom, you're done. I don't tell that to all students, but there's some who just really struggle sort of following all of these negative signs through their problems. My favorite example is potential energy of like a charged particle, and then trying to figure out the voltage, or trying to figure out the potential energy and the negative signs. And there's an integral that gives you a negative sign. There's a negative sign based on where you call the reference, usually at infinity. It can get very confusing, but what's fascinating is when those students are struggling with that, I've noticed that if I just ask them, is this going to be positive or negative? They say, oh, well, it's a positive charged particle. If I bring another positive charged particle close to it, that's going to be hard work done. Right? They get that, but the negative signs in the calculations are driving them crazy. So anyways, I find that really interesting.
Of each object. So I'm going to put minus MA That's going to be the change in energy of object A.
Awesome. Interesting that, it's capitalized in the picture in lowercase in her subscripts. Eventually we run out of letters.
Potential energy of object B.
Cool. Ooh.
And that's going to equal...
Whoa, she moved it. That was great.
Change in kinetic.
Okay, so let's talk about that. Right, so formatting and sort of displaying things on your screen. She absolutely could have, you can see here, right, that it still would have fit. This used to be about right there. So she absolutely could have gone down here. But my guess is so that she protects enough space to finish the problem. She really wants this second line to look like the first line, right? So there's something, and then an equal sign, and then something else. And she's like, man, I'm just guessing here, trying to think about what was going through her head. She's like, you know what? Boom, let's put this down here. Let's put the result we're looking for here. I'm curious if it's all going to fit, right? Because it's probably going to be 1/2 MA VA squared plus 1/2 MB VB squared, though, because they're tied together, VA and VB will be the same. But so really, really interesting. I think that if you're making videos for your students, sometimes your students don't have this flexibility. They've already drawn the picture. They're like, oh, shoot, I don't have enough room. Should I cross it out? Should I start a new page? But that's where you sort of have this mix of, if you've got technology and you think it's going to help your students learn, use it, I say. But I think that she is really putting some thought into what might be confusing to her students, plus maybe sort of leveraging how she wants to use the page. Interesting.
The change in kinetic is change in kinetic of object A Now I don't have to put delta V because it's going to start at 0. So I'm not going to put delta V.
Cool.
I'm just going to put the V that it has at the end.
Cool.
And the same thing is going to be true of object B.
So I said before in another video that writing a velocity squared is actually confusing, right? Because velocity is a vector. How do you square a vector? And so this problem is really about speed.
Because I'm starting at the initial speed of 0, then that means that my change in velocity is actually the same as.
All right. So did you hear that hitch in her voice? She paused in her voice, and I was like, "What's wrong?" But what she was doing was changing her pointer to be a laser pointer. So I have found that to be really useful. In some of the videos that I made a long time ago, I didn't have that. So I just was constantly circling things or like drawing little hitch marks next to it. Like I would come in here and I would go, and it would really make it quite messy. And so I'm now in love with the laser pointer feature in, say, Jamboard. I don't know what software she's using here, but I think that the idea to sort of call the student's attention to something, I mean, you could use your mouse, but I actually think the laser pointer, especially the laser pointer in Jamboard, just going to give a call out to Jamboard, because what the laser pointer in Jamboard does is if you go whoop like this, it shows a little swoop that then slowly fades away. It's kind of like that after image effect in your eyes. Like if someone's shooting a laser, don't do that. Don't shoot lasers right in your eyes. It's really, really interesting as we think about helping teachers really think about what they're doing. Notice what I caught. I caught a hitch in her voice. So that perked me up. I'm like, ooh. And because that's what I want to see. That's what I want to learn from, is that rapid fire critical thinking that people do. She realized, wait, I want to do something different here. I want to shift to my laser pointer. She didn't say, I'm going to shift to my laser pointer now. She just paused enough of her thought to make the change and go with it. So that's the kind of stuff I'm fascinated about.
Is the final velocity. All right, at this point, the rest is algebra.
Well, there's one more thing, right? So there's one more thing that she has to do that that's super important. And so she said all the rest is algebra, but I think there's one more physical thing. So I'm really curious to see when she hits it, she's going to be like, well, of course, da, 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 da. And what I'm talking about is that these two velocities are the same. They're connected by a rope. I'm guessing somewhere in the problem it said a non-extensible rope, a rope that does not stretch on my guess is a frictionless pulley, right? Because we try to give students scenarios that they can start to flex their muscles. Obviously, if you start to make it a flexible rope and a friction more, what if the opposite of frictionless is? Pulley, you have other problems. But there is a major physical concept here, which is that these two velocities are the same. So I'm curious to see how she handles the fact that she already said, well, the rest is algebra.
I stopped at this point because I do want to point out that the two objects, are A and B, are connected by the same string. So since they're connected by the same string, they're obviously going at the same speed. So V,
love it.
Because they're connected by the same
Laser pointer.
Their velocities are the same. And so I end up with that. Now I'm going to...
Ooh, that was cool. So must have done a pause. I actually missed her hitting pause, but boom, just showed up, right? My cursor's in the way. Very cool. Right now there's still a dumb mistake in there, right? So this extra 1/2 shouldn't be there. So I'm really fascinated to watch her fix that too. Because I'm sure she'll say, oh, well, never mind, this is wrong, or something like that. Again, looking for those moments to teach people how to be critical, reflective teachers in the moment, right? So we've got something set up here, but the fact that she just kind of pasted it in was really cool, because it enabled her to sort of finish her thought. That was kind of neat.
Factor out the V squared. Factoring out the V squared, now I'm going to bring the 2 over here, and I'm going to bring that and divide.
Okay, so a couple of really interesting things just happened. Number one, she's again, I believe, pausing her video to paste the results in. What's cool about that is that sometimes it's just pedant, or what's the word I'm looking for? sort of, it takes too long to get to write it all out. And the students are really trying to keep an eye on the big picture. Now, one way to do it is just have all of this already written and just slowly walk the students through it, but that's hard to keep their attention. So teachers for centuries have used, paper to cover things and slowly uncover them. But notice a couple of things happened here. If she had written it out and talked while doing it, my guess is she would have said something about this 1/2, this sort of dangly 1/2 thing. I think that, imagine you're a student and you see this, you're like, wait, what? Well, the question is, you want students to be able to say, wait a second here, and to look up and say, oh, yeah, oh, okay, I get it, right? The second thing, and I know that this would drive a calculator crazy, right? I don't think humans really care, but notice what's missing over here. There's a little square bracket that's missing over here. Mathematica would freak out if you didn't have that there, and so would a calculator. But I don't think that's the sort of thing that's going to drive students crazy.
All right, so I brought the 2 over. I divided by this over here. I brought the 2 over, and then I took the square root of everything.
It's actually really interesting that the square bracket is still missing. Was it a copy and paste? I wonder, can we tell if it was a copy and paste? It's not. This M is different than that M, right? So these are the sorts of things that we all have them, right? We all have these little things that we do, and I've noticed that students start to pick up on it, right? And they maybe make fun of me or whatever if I do something like, for example, students know that anytime I ever write an exclamation point, I make the joke that it's a factorial. So if I say this equals 0, and I'm excited about it, and I go boop, and I put the exclamation point there, the students immediately, because they know that I do it to them all the time, they're like, oh, 0 factorial is 1. And so there's little things, and I love it when my students pick up on that. And so I have no idea if this is a pattern for her, but we've seen twice now a missing closed square bracket. I mean, big deal, right? Obviously, this is going to work out. So I think that it would be fascinating to me if her students were like, well, you forgot that bracket, but in a sort of collegial way, right? Like a way to just sort of joke about it, and maybe even make jokes in their own homework where they don't put it in or something like that. I mean, who knows, right? But I think that we're human, and I think celebrating that humanity when we teach can be really cool.
Now I need to figure out what all the numbers are. So
love
I'm going to
it.
come over to my picture. Obviously, my M's I have. I now have to figure out what my delta H's are. So
Yeah,
I'm
that's the
gonna have
tough
to do
part.
a little bit of math for that. So over here
cool.
I have the triangle that I'm going to use to just figure out delta H of
Cool.
block A.
Cool.
I'm simply going to use trig. I know that it moved 0.25 meters up in this direction.
Okay, we weren't given that before in the
0.25
video, but
meters.
the students knew that.
So I use trig to solve for delta H, and I find out that it moved up 0.15 meters.
All right, let's see here. I'm going to make my estimate here. So 100 kilograms, that's like me. Yes, stop judging. If I were to move 0.25 meters, quarter meter, it's going up a few steps. I'm going to say this is between 1 and 10 joules, just off the top of my head. I'm going to be wrong.
Meters.
Let's see.
All right, so the 0.15 meters.
Oh, we don't care about joules. We don't care about joules. Sorry, I just, who cares about that? We want to know how fast I'm going to be going. So if I fall 0.25 meters, so that's almost what's sort of in here. If I fall, so quarter of a second, half a second, something like that. It's going to be slower than that, though, because this 50 kilogram thing is dragging me back. So I'm going to say it's going to take a couple of seconds, 2-3 seconds, like that. And I would say that at that point I'm traveling quarter meter in a few seconds. So it would take me maybe 10 seconds. I'm going to say between 0.1 and 1 meter per second.
That is represented by delta H. Is going to go right here.
Look at that!
Ooh, I didn't grab it all.
That was cool, though.
Now looking back at the
Oh,
picture,
that's super
if
cool.
the
Saving a lot of
object
space.
A
Saving a lot of
went
space.
up by this much, the string moved by this much. So if the string moved by 0.25 meters, then box B moved down by 0.25 meters.
Yeah.
So
Boy, the
this
signs here.
distance, this
Interesting.
movement down is this one, 0.25 meters.
And that's what I was talking about before. Students will know which one's sort of contributing to getting it faster, which one's kind of slowing it down. They're going to know that the contribution between these two terms is going to be opposite. So there might be some niggly negative sign out here, but I would guess that most students would have a good sense that these are fighting against each other, so they should not cumulatively add. Probably this will be a negative sign.
So here, this movement, this delta H is 0.25 meters, but in what direction? Down. So I'm going to put that in as negative 0.25 meters. Where? Right in there.
Cool. Cool.
Plugging and chugging is going to give me a V equal to the square root of 2.31, which is 1.5.
Oh, I said between 0.1 and 1. All right. Let's see. Oh, you can tell I'm doing a lot of searches for physics things, and you can tell I'm watching some election, and you can tell that I'm a bicycle fan and a jazz fan. Apparently Saturday Night Live I click on. Oh, you should definitely check out the Zildjian Live thing. And this is a video that I watch over and over and over again. Super awesome song. Take a look. Sean Martin, Yellow Jacket, covered by Dream Session. Oh, yeah, and I'm really, really bad at mountain biking. Anyways, you guys, I'm just going to back this up a tiny little bit for
Is 0.25.
just to talk about just some of the wonderful things we've seen here. I really loved the color. I loved the literally moving numbers in or pointing it in. I think saving a little bit of space so that she didn't have to go to a blank screen by just sort of pasting stuff in was very, very cool. You heard me try to do some arithmetic in my head. I was sort of close, not great. So I think that all in all, very, very interesting, and I think a tricky problem. A couple things in it are a little bit tricky. So that's it for today, everybody. Thanks so much. Have a great day, and remember, physics teachers are awesome.